Assalamualaikum and hi doctor. My name is Muhammad Nuri Kemal bin Amdan, also known as Ikmal, and my group will be discussing about the calcium oxide as the improvement catalyst. My group consists of 5 members, which is me, Ikmal, Daniel, Lily, Anis, and the last one Izzat. As I mentioned before, my group will be discussing about calcium oxide. Now, let's look further on how calcium oxide, which is current catalyst, will be synthesis. The raw material of the catalyst is either limestone, calcium carbonate or calcium hydroxide. The main process of calcium oxide synthesis is the calcination process. Firstly, the limestone will wash by the deionized water in order to remove dust and impurities that might be present on the surface. Then, it is dried overnight in an oven at 105 degrees Celsius. Then, the dry limestone will crush, sieve, and further calcine at 900 degrees Celsius for 1 hour 30 minutes. At 900 degrees Celsius, an optimized calcium oxide catalyst can be produced, which will then indicate the evaporation of water and carbon dioxide, the surface area of the catalyst form, and the catalyst activity. The same procedure was carried out to synthesis calcium oxide catalyst using calcium carbonate and calcium hydroxide. However, limestone is more preferable as the raw material for the synthesis of calcium oxide catalyst, as it gives a higher performance than the calcium oxide catalyst prepared from other raw materials. These are the advantages of current catalysts, which are non-corrosive, found abundantly, promotes long catalyst life, easy to handle, react relatively faster than acid catalyzed transesterification reaction, high catalytic activity, reusable, requires milder reactions conditions, easy separation from mother liquor, and lastly, eco-friendly. And here are the drawbacks. Firstly, leaching of calcium ions. Next, dissociation of calcium oxide with methanol. Require a vacuum or nitrogen atmosphere. Easily saponification. Require thermal activation. Lastly, sensitive towards FFA content in the oil. Now, we are moving to improved catalyst, which is calcium oxide loaded with alumina. Impregnation and calcination is the catalyst synthesis method for improved catalyst. First, calcium acetate with a mass ratio of 1:1 to the support is dissolved in 50 ml of distilled water. Next, stir with 40 grams of alumina at room temperature for 4 hours. The obtained slurry is heated up at 100 degrees Celsius in an oven overnight to remove the water. By using a muffle furnace, the catalyst is calcined in air at 718 degrees Celsius for 5 hours. Lastly, the catalyst is kept in a desiccator in the presence of silica and potassium hydroxide pellet to avoid water and carbon dioxide contact with the catalyst. The first property of improved catalyst is mesoporous catalyst. Calcium oxide loaded with alumina is a mesoporous catalyst that has a large specific surface area. Next, it has high amount of active sites concentration, which can provide enough active sites and pores. Then, gamma aluminum oxide has high thermal stability and specific surface area. The last property is calcium oxide is cheap and non-toxic precursor and also has high basic value and not easily soluble in biodiesel products. Now, we are moving to the catalytic reaction. Reaction condition for this reaction depends on what catalyst is used. If bulk calcium oxide catalyst is used, the methanol to oil molar ratio is 15:1 and in the range of 6:1 to 24:1 if we use the calcium oxide loaded with alumina. Catalyst loading in weight percent for bulk calcium oxide is 2.5% and 1 to 8% for loaded calcium oxide. There is not much difference for reaction temperatures. Bulk calcium catalyst use reaction temperature of 338 Kelvin and loaded calcium oxide catalyst use temperature range from 300 228 to 338 Kelvin. The reaction with calcium oxide loaded with alumina can be optimized by improving the reaction conditions. Central Composite Design (CCD) can be applied. The methanol to oil molar ratio is 12.1 to 1 and temperature is 337.4 Kelvin. 3 mole of alcohol and 1 mole of triglyceride produces 3 mole of ester and 1 mole of glycerin in the stoichiometric reaction. In reality, extra alcohol is consumed in order to boost ester synthesis. Preparation of the feedstock, rate of reaction, phase separation, dehydration, alcohol recovery, purification of the ester and glycerin are all part of the transesterification process for biodiesel processing. The reactor is the most important part of the transesterification process. The reactor is used to heat the oil and mix it with the alcohol and catalyst. The method of preparation is designed to reduce acidity and moisture content. After a neutralizing operation, the drying and dehumidifying activities are carried out. After the transesterification procedure, centrifugation is used to separate the two phases of glycerin and esters. Because esters are light, they float to the top while glycerin sinks. Ethyl or methyl esters are refined to generate biodiesel and meet the requirements of set technical standards through centrifugation and dehumidification. The yield of produced biodiesel in the transesterification reaction is influenced by several important parameters. If FFA concentration exceeds 1%, the two-step transesterification is needed. If we use 9:1 methanol to oil ratio, 2.8% weight per weight concentration, 60 minutes at 65 degrees Celsius, it will give yield 77.3%. This is the references used to discuss about this topic. That's all from me. Thank you.